Hello, my name is Snežana, as you have heard, and I would first like to thank Nenad in particular for inviting me to this very nice conference. It's always nice to be back here in my hometown. Yes, today I will talk about a little bit different topics. So we are dealing here, just let me find the pointer, I guess it's this one, yeah. So we will talk about, quantum things. So we are now in a quantum domain, and we want to use the sound, as I will show you later, to encode information in a specific way on photonic qubits. And this, of course, is quite important for future quantum technologies and especially for secure quantum communication. Now, this work was performed in my home group at the Department of Physics of Materials at the Autonomous University. So Sanja had a talk also a few days ago. It was a collaboration with other researchers from Polytechnic University, also in Madrid, who provided the samples that we used in these experiments. Here, as I already mentioned, we are dealing with non-classical or so-called quantum light, and it is interesting because it can be manipulated at its fundamental single photon limit. So this is actually essential for quantum communication and information processing that is already taking us well beyond today's classical digital landscape. And the way it is done is by providing some interesting applications like quantum teleportation or quantum cryptography, which enables quantum internet that is basically leading us to unconditionally secure transfer of information, as well as quantum computing using photonic qubits, that is capable to increase computational processing power, as you know, exponentially compared to the classical machines. So the production of quantum light states is a very competitive research field, as you know, and various solid-state systems have been investigated over the years, including atoms, organic molecules, atomic defects in inorganic crystals, like, for example, color centers, or, as of recently, defect states in two-dimensional materials. But here, in this work, we are going to focus on semiconductor nanostructures, and in particular on epitaxially grown quantum dots, which have been around for more than a decade, and have been shown to be a promising physical system for quantum light emission. And this is basically due to their scalability and integrability with the existing semiconductor technologies, like, for example, widely used silicon-based technology. So in this work, we use group 3 nitride semiconductor material, which basically gives us some advantages compared to other semiconductors, and this is high temperature operation of the devices, as well as wide spectral tunability that goes from deep ultraviolet to telecommunication wavelengths. So therefore, it basically spans the entire solar spectrum. Now, having the 3 nitride quantum dots, or quantum emitters, that are operating in the UV to visible spectral region is particularly important because of their scalability and because of the possibility to have free space communication, which is much easier than using fiber optics as it is done today. And also, in their word-side form, these group 3 nitride semiconductors favor the emission of linearly polarized light, and this is vital for various polarization encoding quantum information protocols, like, for example, quantum key distribution or linear optical quantum computing using photonic qubits. So all these and many others advantages are highly beneficial for practical applications of different quantum technologies. So indeed, there have been a lot of advances in this field with all these different systems that I mentioned, but there are still many challenges, and the one that I would like to focus here today is how to efficiently encode information onto photons. As you know, photons are excellent carriers of quantum information. This is one reason, because they only weakly interact with each other and with the environment, and also because they possess a number of information-carrying degrees of freedom onto which we can encode information, like, for example, polarization, photon, time binning, orbital angular momentum, frequency phase, etc. Now, in most current quantum communication protocols, we are using currently polarization as a degree of freedom. And what we are doing is we are converting qubit of informations onto different photon polarization directions, like, for example, horizontal or vertical. However, this type of encoding has a significant issue, which is depolarization and decoherence, and that, of course, introduces a lot of losses, and it's not good for quantum communication technologies. So in order to overcome this, we are here proposing a different way to encode qubits of information, and we are doing it onto photon emission or arrival time. So this type of encoding is quite robust. So it therefore allows to encode a large amount of quantum information onto single photons, which of course is of quite relevance for quantum communication and information processing. So here I will be addressing this challenge. Going further, so what I will talk about in this presentation is I will show that we can generate linearly polarized single photons in the UV to visible spectral range using gallium nitride nanowires, which are hosting indium gallium nitride quantum dots. So I will first show you the optical properties of our sample that were characterized by microphotoluminescence spectroscopy, and then some experimental evidence of the emission of single photons from these quantum dot states. And then you will see that we can use surface acoustic waves to control dynamically in real time the photon emission wavelength to trigger its emission time, which is not only important to create on-demand single photon sources, but it can also be used to encode information on the photon emission time, as I will show you later. So the three nitride nanowire heterostructures that we used, as I mentioned, were grown by our colleagues at a different university in Madrid, and this was done by plasma-assisted molecular beam homoepitaxy using selective area growth technique that was achieved by colloidal lithography. And as you can see in this scanning electron microscopy image here, these nanowires exhibit such hexagonal cross-section with these lateral facets defined by the non-polar M planes. You also see that the top of these nanowires has such pencil-like profile that is defined by the semi-polar S planes. And actually, the structure or the morphology of these nanowires is core shell, which means that there is a thin indium gallium nitride shell that is embedded inside the gallium nitride nanowire, as you can see in this illustration. And as it was confirmed in transmission electron microscopy characterization of individual nanowires, we see that this thin indium gallium nitride nanoshell is formed on different crystallographic planes with different orientation. So as you can see, we have here top polar facet, then semi-polar side facet, and lateral non-polar. So as I will show you in the continuation, all three sections of these nanowires contain quantum dots that are responsible for the emission of single photons. Now, this is actually the first experimentally demonstrated nanostructure, single nanostructure that is capable of simultaneously hosting quantum dots that were grown on different crystallographic facets, so with different crystallographic orientation. Now, having semi-polar and non-polar quantum dots or quantum emitters is of particular relevance in order to boost the operational speed of quantum light devices, and this is because the strong polarization-induced electric field, which is typically present for quantum dots that are grown on these polar C planes, are absent for the low polarity planes, and as a result, the recombination lifetime is reduced. Therefore, the photons are emitted at much higher repetition rate. So in order to manipulate our nanowires, what we use are the so-called acoustic waves. We actually use the strain and the piezoelectric field of this acoustic wave that propagates along the surface of a strongly piezoelectric material. So in this case, we use the so-called acoustic delay line, which consists of two metallic interdigital transducers that were lithographically patterned on lithium niobate crystal. and the acoustic waves are then excited electrically by applying a radio frequency signal onto one of these IDTs, which for these particular experiments were designed to operate at around 300 megahertz frequency, but this is only as a proof of concept. Actually, the IDT resonance frequency can span a wide frequency range from a few megahertz to several gigahertz, and this basically depends on the design of the IDT, so we can easily change it. Now, the use of such highly piezoelectric substrate provides strong strain and piezoelectric field, which we can then use to dynamically, in real time, control the mechanical, electronic, and optical properties of whatever nanostructures that we deposit on the surface of this acoustic delay line, as it was previously shown in different semiconductor systems. So what we basically did is we mechanically removed the nanowires from their native substrate, and we dispersed them onto this acoustic propagation path in between the two IDTs. In this way, we obtained low density of these dispersed wires, so we could, in principle, perform single nanowire spectroscopy. And we then basically analyzed their luminescence using a direct optical illumination by a focused laser beam. So, as a result, we obtained this spectrum, which is representative spectrum of the low temperature micro PL measurements on a single nanowire. And as you can see, there are these 4 distinct emission bands. This higher energy luminescence is due to the near band edge emission from the gallium nitride nanowire body, whereas these other 3 bands correspond to different sections, so polar, semi-polar, and non-polar, of the indium gallium nitride nanoshell. And not only that, but this spectrum also reveals the presence of such intense and narrow emission lines, which are superimposed on top of these 3 contributions from indium gallium nitride. We observe them up to some 80 Kelvin. The idea is to go further to room temperature, and we attribute these lines to quantum dot states, which are most likely induced by exciton localizing potentials due to fluctuations of indium content across this indium gallium nitride nanoshell. We also performed the polarization resolved PL measurements for all type of quantum dot states, polar, semi-polar, and non-polar. And as you can see, they are all linearly polarized with the average polarization ratio above 70%. So this high degree of linear polarization can be ascribed to a particular anisotropic structure of the quantum dot confinement potential concerning both its strain and its shape, basically, as it was previously reported for non-polar and polar indium gallium nitride quantum dots. Now, only the fact that we are dealing with linearly polarized photons here means that we can already use this system for polarization and coding quantum protocols, but as I said, there are some difficulties with this type of encoding. So to actually confirm that we are dealing with quantum light, what we did then is we studied the statistics of the emitted photons, and we did it by filtering the luminescence from these nanowire quantum dots using a grating monochrometer, and we then directed it to a standard Humbury, Brown, and Twist interferometer that delivers such histogram of correlation events that is proportional to the photon correlation function. So in the case of truly single photon emitter, as it is seen here, what we observe is this complete reduction of the G2 function at 0 time delay between consecutive photon detections at both detectors. And indeed, for all types, so 3 types of quantum dots, we do see such reduction of coincidence rate at 0 time delay, which suggests that the probability of simultaneous multiple emission or emission of multiple single photons is significantly reduced. So actually, when we correct these measurements for the limited temporal resolution of our measurement system and for the presence of these background photons for practically all studied nanowire quantum dots on each crystallographic orientation, we obtained the G20 value well before below the 0.52 photon threshold. And this is a clear signature of single photon emission. So now we come to, I would like to show the effect of the acoustic wave on these nanowire quantum dots. So for that, I will focus only on the polar quantum dots in this topmost nanowire region. And here you see again a low temperature PL spectra, which shows you in the absence of the acoustic wave, such sharp lines. They correspond to the excitonic complexes, which are originating from one of these probed nanowire quantum dots. Now, this exciton and bi-exciton assignment was confirmed by excitation power dependence measurement, which, as you can see, shows linear for the case of exciton and quadratic for the case of bi-exciton dependence of the integrated peak intensity with optical power. And this is also confirmed by polarization resolved measurements, which show here that these two emission lines are collinearly polarized with a similar degree of polarization as it is expected from the exciton and bi-exciton originating from the same quantum dot confinement potential. So now when we apply the acoustic wave, this spectrum undergoes this apparent splitting of the two lines, as you can see here, and this splitting increases continuously as we increase the acoustic power or the RF power that we apply to the IDT. So these experiments actually show that we can efficiently use surface acoustic wave to fine-tune the quantum dot emission energy within some bandwidth of around 2 milli-electron volt. Now, this is actually an important result because with this, we can tune the emission energy of these similar quantum dots and force them to emit at the same wavelength, which is quite important for all quantum communication and computation technologies. So these changes, the spectral changes that we observed on the previous transparency are basically due to periodic shifts of the quantum dot energy levels that I illustrated here, and this is induced by deformation potential coupling between these emitted states and the oscillating acoustically induced mechanical vibration. So in other words, as the acoustic wave propagates and it couples to the nanowire, the embedded quantum dot is periodically strained, so its transition energy oscillates sinusoidally, as you can see here, in such a way that it changes from minimum to maximum value with respect to the equilibrium energy, this one here, in the absence of the acoustic wave. You can also see this, it's very evident, in the time-resolved stroboscopic measurements, which are performed under pulsed optical excitation, which is synchronized with the acoustic wave. So we can clearly see that during the decay of this transition, it has sinusoidal modulation. Now, if we average this in time, we will again observe the previous transparency, like splitting of these two lines. So now the stroboscopic experiments, which are performed at the time resolved pulse log detection in this case, we also see that when we apply the acoustic waves, during the decay of these exciton and bi-exciton complexes, we do observe some small changes in the intensity of these peaks, like you can see here. So if we follow the slow PL decay, such as that of the exciton in the absence of the acoustic wave, we see that these oscillations appear twice per acoustic cycle and that they take place at well-defined phases of the acoustic wave, so this one, which basically correspond to the maximum value of the longitudinal piezoelectric field component of the acoustic wave, which is marked by these red arrows here. So in principle, the amplitude of this oscillation, of course, scales with the acoustic power, with the acoustic amplitude. So what we then did, we increased, here, oh no, going back. So we basically increased the RF signal in order to get stronger this longitudinal field value, and also we deliberately now apply complex periodic waveforms, so not anymore sinusoidal, which we can track by the response of a nanowire quantum dot sensor. Now, you see here that this oscillation in the intensity are much more pronounced, and again, you see that they exactly follow the form of this longitudinal piezoelectric field component. So we basically conclude that these intensity oscillations are a result of the periodic field-assisted simultaneous transfer into the quantum dot of the electrons and holes that are optically generated in the surrounding region, so around the quantum dot, in this optically probed nanowire apex. So in principle, this result can be combined with spectral filtering that is basically achieved by collecting the photons, as you can see here, in a narrow energy range. So we can basically decide at which energy to collect these photons. And in this way, we can obtain more complex temporal sequence of the emitted photons. So here, I show one sequence, here another, depends on at which energy we, as I said, collect these photons. So in this way, we can basically encode information into the photon emission time. So we use the photon emission time as a degree of freedom here. So the advantage of this method over other schemes is its resilience, of course, which basically makes them better suited for fiber optic applications, which is what we mostly use today, as opposed to, for example, polarization encoding. So this brings me to my summary. So what I have shown here is that we can generate single photons, which are highly linearly polarized, by using gallium nitride quantum dots that are grown on polar, semipolar, and non-polar facets of epitaxially grown gallium nitride nanowire. And I have also shown that these quantum dot states are quite sensitive to the propagating acoustic fields, and that this can be used as an effective method for the in situ control of the photon emission wavelength and its emission time. And by combining these two, we are basically able to encode the qubits of information onto photons emission time. So this, of course, is quite important for the integration of such quantum dot systems into future on-chip quantum technologies. And with this, I would like to thank some other colleagues who also contributed to these experiments, as you can see them listed here, and to the Spanish Ministry of Science, Innovation and University for their financial support, and of course to thank you for your attention. The free space. Yeah, usually in the UV. So there's another atmospheric window, which is in the UV. So UV light actually is much better for, there are very little losses. Chinese people are already doing that, but it is in the UV part. So, so far, only the UV can be transported through free space. Sorry? Oh, quite far. They can actually do it like 1,000 and something kilometers between Beijing was the first experiment and the satellite above it. So satellite through free space, yeah.
Technical curiosity. What is the size of the device?
Of the transducers?
No,
it can be aluminum, titanium, aluminum, can also be gold, it depends. So the size, there are these fingers, so the spacing of the fingers is going to determine the frequency of the acoustic wave. Now it depends, if we are talking about micrometer or a few hundreds of nanometers, we can do it with optical lithography or E-beam, but sometimes we need even higher frequencies, which means like even 10 nanometer separation between them, which is very small, in which case separate, exactly, which then requires nano-imprint lithography, for example. But that's to go to higher frequencies. And of course, the frequencies are not the same in each material because the sound has different velocity. So it depends also on that, depending on the material. Lithium niobate we use. Lithium niobate because it's highly piezoelectric, but one can use aluminum nitride, for example, which is also highly piezoelectric. So we just use this because it's commercially available. So then you can cut it and you can produce this lithographically, these IDTs on top. Yeah. Mm-hmm. The quality of? Well, the quality is also important, of course, because of the coherence later of the emission is going to depend also on the quality of the nanowires. It is important, but this is grown by molecular beam epitaxy, and they are really of good quality, as the transmission electron microscopy shows. So there's no strain, for example, they're free of strain, so the quantum dot does not experience any strain in this case, because it's in the top region, and so yeah, I would say it's important. Plus also, but we have to bear in mind that the quantum dots themselves here are induced by the fluctuations of indium, which of course you will always have when you grow epitaxially indium gallium nitride, right? Because indium is a larger atom, it's always going to tend to go to the surface, so it will tend to cluster, which is in this case the reason why we have quantum dots. Now that's not very controllable still, so yeah. Thank you.